Yeah, so we're talking about standing waves. This is what happens when two waves that are identical are traveling in opposite direction and they interact. And so this is an example of a standing wave here. The top wave is moving to the right, the bottom wave is moving to the left, and we can see what happens when they add. So when they perfectly overlap, you see that the magnitude doubles, sorry, the amplitude doubles. And then you see when they perfectly like overlap, but in the opposite way, they cancel out and you get zero amplitude. And so this is a standing wave, and it's called a standing wave because it doesn't look like it's actually moving, right? It just looks like it's kind of just oscillating up and down, but not traveling left or right. And even though we know waves are supposed to travel. So let me go back to the lecture notes. You can close out of that now. Yeah, students from 9A last quarter will remember that often I'll forget to record, so please remind me at the beginning of lecture if I don't. So let's try to characterize what a standing wave is mathematically. So we do that by writing down an equation or a wave function for the standing wave. So mathematically, what do we have? By the way, sorry for the technical difficulties today. It's always happens when you need it to at least happen. So let's say that let's imagine the right moving wave is F1. It's described by F1. Well, we know it's going to have some amplitude, and according to the picture that I showed you, it's a sine wave or it's a harmonic wave. So this will be described by cosine. Now we don't know what the wavelength is or the period is, so we can just write the general form 2 pi x over lambda, and it's moving to the right. So we have a minus 2 pi t over capital T plus say phi 1. And then we have F2, this is the wave that moves to the left. We said it had to be identical, except it's just moving to the left. So we have the same wavelength, but this time it has a plus sign because it's moving to the left. And maybe it has a different phase constant. That actually doesn't matter. So this is our right mover. This is our left mover. All right, so let's just, for the sake of argument, let's just assume that phi 1 or phi 2 minus phi 1 is pi, i.e., just assume that they initially start out of phase, right? That means that if you plug in x and t equals 0, the F1 will be pi further along in its oscillation than F2 is. Sorry, F2 will be pi further along in its oscillation than F1 is. What that means is it starts out destructively interfering because pi is precisely 1/2 of an oscillation. So while one might be at a peak, the other one would be at a trough because that's precisely 1/2 later. If that's the case, then what we get when we add up x1 and f2, f1 and f2, sorry, which is what we do when we're talking about waves overlapping, is we just get the following. And this is a result from just trigonometry that you guys could derive if you wanted to. I'm not going to do so, because it takes a little bit of effort, but just go look up some formulas for trig functions, basically. There's a Wikipedia page that will have that. So this is the formula. Sorry, that should not be equals, that should be plus. This is what you should get if you were to add these two waves, assuming they have that same initial phase. Now, keep in mind that if this initial phase difference was, if it was something else, it wouldn't really change the overall structure. You would still get a part that's oscillating in x and a part that's oscillating in t, but it would just be a little bit more complicated. You would have some phases thrown in. So this is just the simplest way to show it, but it doesn't actually matter. Now, there's a few things to note here. First, the amplitude is doubled. So the maximum height is twice as large, and that shouldn't be surprising. When they perfectly overlap with each other, the height should be twice of the height of a single one. And notice that all you have are sines and cosines here, and all you have are cosines here. So the maximum height of those without the a, that's just 1, because a cosine can be at most 1. So the amplitude here is, or the maximum height is 2a, whereas the maximum height for either one of the individual wave functions is just a. Again, not surprising. This first term is a snapshot of a wave, right? Not span shot. It's a snapshot. For example, look at, say, this top wave. if you just imagined that t equals 0, what would it look like? Well, it would look like a cosine that varies in x, and it is shifted in one way or another. But all this part is, the part that I put a bracket around, that is just something that depends on x. You could just plot that on an x-axis. It would just look something like this. And then similarly, you could ask, what is happening here? Well, this is the oscillation. This characterizes or describes the oscillation of a single point. Right? Remember how we described periodic functions or periodic waves? We said that you could either imagine it as, you could either view it as a snapshot, or you could view the oscillation of a single point. And so this still describes, this combined wave function still describes a wave, because a periodic wave at that, because you can, if you set t to some constant, you get a snapshot, and if you set x to some constant, you get an oscillation of a single point. And further, you can kind of then imagine what's happening. If you imagine that this term, the term that depends on time, is kind of a time-varying amplitude, then what you get is you get a wave function, or you get a function in x that looks like this, and say this is f, but the height depends on t, and the height is getting bigger and smaller. And so that's what a standing wave is, right? It just sits there, but the heights shrink and get bigger, and it flips signs as well, because the amplitude becomes negative, and so on. But so it's a nifty way of visualizing a standing wave. So often when you see this type of wave combination, which you'll see an example of in the homework, where you have the sine of something, or the cosine of, the sine or cosine of x times the sine or cosine of t, that is a standing wave. Now, there is something to note here, that this is not actually a single wave. Now, any single wave can be characterized as being written as f of x plus or minus vt. But this one cannot. Oh, come on. Right? But, however, it is still a wave. It's just a superposition of two waves. And you'll find that if you were to plug this into the wave equation, again, which you're going to do something similar to it on the homework, you'll find that it still satisfies the wave equation. And so what's happening here is that in order to be able to write a wave function as in this form, f of x minus or plus vt, the wave has to be traveling in either the positive or the negative direction with that speed v. However, in this case, you have the combination of a wave traveling to the right and a wave traveling to the left at the same speed. So there's no way to write it in this particular nice form, but it will still satisfy the wave equation, because the wave equation doesn't care about what direction the wave is traveling in. It only cares about, does it have a constant speed, and is the second time derivative proportional to the second spatial derivative? And that's still true. So this is called a standing wave. It's not a traveling wave. And perhaps the correct way to describe functions that have this form are traveling waves. By the way, there are other formulas for standing waves. There are other ways to write it. This is just one particular example. So far I've given you a very, not arbitrary, but a very special set of scenarios that needs to happen in order to have a standing wave. But standing waves in nature do occur. Like they are things that happen in real life. For example, there is this phenomenon known as wave reflection. And wave reflection is a very easy way to generate a standing wave. So let's look at an example. We have a rope that is tied to a wall at one end. So imagine like you're holding one end of a rope and you're wiggling it up and down. And on the other end of the rope, it's like tied to a wall or something. So obviously you're sending waves down one direction, right? You're sending waves as you wiggle them down, and you'll send waves down one direction. But what happens once it hits a wall? Does it just stop? Well, no. In fact, you have the wave actually reflects off of the wall. And so let me show you a GIF of this. By the way, it's pronounced GIF, not GIF, and anybody who says otherwise is free to leave the course. Let me just, here we go. Here we go. So here's an example. Hopefully you guys are seeing the, is it? Oh no, I want this one. Hopefully you guys are seeing the wave reflection. So you send a wave down, and then it reflects off the wall. Yeah, I will fail you if you say it the other way. It reflects off the wall, and then it inverts. So that's a very, very particular phenomenon, right? It doesn't just reflect, it doesn't just bounce off and come back the same way, it actually inverts, and that's important. That's a property of the fact that the right end of the rope is fixed, meaning that it's not allowed to move. There's another example that I can show you in a second. Let's say that you have a rope tied to a ring on a pole out one end. So the thing to imagine here is, first you have to imagine there's no gravity, by the way, because otherwise a lot of these things don't work. You have your string, you're holding it on one end, and on the other end, it's like tied to a ring that goes around a pole that can go up and down. So you flick it, and then as it goes to the pole, it can't keep traveling forward, but it can move up and down. So let me show you an example of that. Let's get it to load. Right, so here's an example. So you send your wave in, and then because it can't keep going down, the ring just goes up. And then as the ring comes back down, it's pulled down by the rest of the wave. It reflects off and goes back the other way. So in this case, unlike in the other case, the wave stays upright instead of inverting. And again, that's an important distinction. That's because the wave was allowed to move on the, it was allowed to move on the wall. However, do note a specific property of the wave as it's connecting to the ring, right? The slope of the wave as it's attached to the ring always stays 0. That's the boundary condition, i.e. the boundary condition, I'm putting in air quotes, that must be satisfied in order to have a soft reflection, which is how this is characterized. The slope is 0, whereas in the hard reflection case, where it was fixed, the displacement was 0. So those are the two distinctions. If you have 0 displacement, that is called a Dirichlet boundary condition. You don't have to know this, it's just general physics terminology. And if you have the slope is 0, it's called a Neumann boundary condition. Anyway, those are both useful facts, but those are a way that you can generate standing waves from reflection. So let me summarize this. In words. And so then you guys can take notes, because I know it went over that fast. So the leading edge of an incoming wave, and this is incoming to the reflecting surface, whatever that is, it's a wall or a pole or whatever, of an incoming wave is the leading edge of the reflection. Now, let me be specific, let me explain that a little bit. Let's say you have a wave that's shaped like this, right? Let's do this right. You have a round hump and then a pointy bit, and it's traveling this way. And then here's your reflecting surface. Let's assume it's a hard reflection just for, oh, that's crazy that there was just an earthquake. Okay, well, I'm glad everything's okay. I've lived in California for 5 years. I've never experienced an earthquake while I was awake. So anyway, so this wave comes in, and so when I say leading edge, I mean the pointy bit. The pointy bit is the leading edge, so that should be the part that comes out from the wave after it reflects. So what we're left with is we're left with something that looks like this. Let me get this right. It would look like this coming back. Remember, it's a hard edge, so it would be inverted when it's reflected. However, the fact that the shape of the leading edge is the shape of the leading edge of the outgoing wave, that shouldn't be surprising, right? The edge that hits the wall first should be the edge that reflects first and thus comes out first. that's just like causality, right? That's just how things work. Like things happen in a particular order. If the wall hits, if the one part of the wave hits the wall first, it should be reflected first. So the important part is that it's not reflected just like backwards going this way. The actual waveform of the wave itself flips direction, end over end. Another feature is when reflecting off of a fixed wall, this is that quote unquote hard reflection, the wave is inverted. And so that, again, that's the feature that you saw in the GIF that I sent you. And for a free wall, this is the soft reflection, where the wave's waveform is allowed to move up and down on the wall. The wave is not inverted. Now, there's a way to, how do I want to say this? There's a way to imagine this, right? There's a way to understand this, but it relies on the boundary conditions that I've provided you. It relies on this business of either the displacement is 0 or the slope is 0. So let's just do a quick thought experiment to explain this. So the most straightforward way to explain this is that imagine that there's a ghost wave. And by that, I mean, it's not a real wave, but it's kind of like a wave, just like how you can imagine that there's like a ghost in the mirror, or like an imaginary thing in the mirror. Imagine that there's an imaginary wave on the other side of your wall. So this ghost wave will allow us to satisfy the criteria that we need. For a fixed wall, we know that we need to have destructive interference at the wall, because we know that the disturbance or the displacement has to be 0 at the wall, right? That's what it means for it to be fixed. For the free wall, the criteria that I gave you is that the slope is 0, but you can actually relatively easily show that that's equivalent to constructive interference. I'm not gonna go into a whole lot of detail as to why that's the case, but it should be, hopefully you guys can at least remember from the GIF that it's it's constructive interference. So we need constructive interference at the wall. So the idea is that you just imagine that your wall projects out, or has a ghost wave on the other end that does what we need it to do to get those properties right. So here's your real wave on the left coming in, and then you have your ghost wave on the right going in. And so the point is when these two waves come and overlap, because of the superposition principle, you would always have 0 displacement on the wall, because they're perfectly inverted versions of each other. And this also explains why the leading edge coming in is the leading edge going out. And so this will ensure that that you have 0 magnitude at the 0 amplitude at the wall, and it explains why the wave is inverted off of a free wall. Similarly, for a free wall, this is fixed. For a free wall, if we have the same waveform, we know that we have to have constructive interference at the boundary. So in order to have constructive interference, you have to duplicate the wave, and it can't be inverted. So when this comes in, they will add up, and they will double in height and so on. But eventually, the ghost wave will pass through, and it will be not inverted. Now, again, I have some more animations for you guys from GeoGebra. Very useful visualization tool. Let's see if I can get this to work. Come on. Zoom out a bit. All right. Let me show you. All right, so this is just a nice little animation that some guy designed. So I'm going to show you the wow, it's very slow. I promise it's not just my tablet. So this is for a free end, but I want to show the ghost wave. Okay, this is not doing what I wanted it to do. How about I show you this? Let's see if this is what I want it to do. Okay, so it's not ideal. What it's trying to show is that the waves just pass through each other as if there wasn't a wall there. But we simulate the wall, or we match we match exactly what the wall does by imagining that there is no wall, and instead you just have this ghost wave doing this thing. And like in physics models, it doesn't really matter how you analyze or how you understand the phenomenon. If your model can account for whatever phenomenon you're observing, then it's a perfectly valid model. So the thing to imagine here is just that the real way is that instead of a wall, you could just precisely imagine there is an identical wave coming in and interfering. That's a perfectly valid way of understanding any sort of boundary. Now, it's not just physical walls or poles with a ring around them that do this. In fact, you can get reflections off of other things. Anytime you have a change in medium, you also get a reflection. It's just the question is what type of reflection? So remember that the medium is the thing that determines the wave speed of your wave, right? It's properties of the medium. For example, on a string, it's the tension in the string and it's the linear mass density of the string. Those are the things that determine the wave speed. It doesn't have anything to do with the waveform that is propagating in that medium. So the way we can characterize, oh yeah, you should be seeing the OneNote, sorry. Yeah, I only wrote one sentence. It's not just walls, we should have medium changes that also cause reflections. So the point I was making is that the way we can characterize a medium change is when you have a change in wave speed. Now, for a wall, the wave speed is 0, right? The waves just don't propagate on the other side. You can imagine walls as basically very special cases of medium changes. However, well, depending on the type of wall, if it's a fixed wall, then it would be it would be a wave speed of 0, and if it's a free wall, it would be a wave speed of infinity. The whole point is that, let's say that you had 2 strings, and I'll give you an example of this in just a minute. Let me characterize the properties, what happens when you have different medium changes. So when a wave goes from a fast medium to a slow medium, the reflection that occurs at the interface is inverted. Alternatively, when a wave goes from a slow medium to a fast medium, and when I say fast versus slow, what I mean is the wave speed being faster than one wave speed being faster than the other. The reflection is not inverted. So in the example above, imagine for a fixed end, or for a fixed end wave, this is like a rope just tied off on a wall. You can just imagine that the wave speed in the wall is 0. You have no wave propagation at all. And so you would get an inverted wave coming out. And then for the free end, that's a special case of a wave speed being infinity on the other side. So you have an upright wave coming out. Now, again, I have some more animations for you. These will all be posted on Canvas, by the way, or at least they'll be linked to in the notes. here is a reflection off of, I haven't shared it yet, but it's still loading anyway. Here's a reflection off of a slow medium. So first, let's look at this. Look at the wave speed in the thinner rope, as opposed to the thicker rope, right? The wave speed in the thinner rope is definitely higher. And so what do we see? On the reflected wave, well, certainly some of it gets through. That's true, but we're not worried about that yet. On the reflected side of the waveform is inverted. And that's because it's going from a high speed to a slow speed. Alternatively, we could look at the same type of animation, but we have a thick rope going to a thin rope. Notice, first of all, that the thick rope is going at a certain speed and the thin rope goes much faster. And then look at the reflection on the thick rope. Again, you have an upright wave indicating that you went from a slow wave speed to a fast wave speed. By the way, the amount that's transmitted, that's something that depends on other more complicated things. So we're not going to talk about that a whole lot, if at all. But note that it is a property of the interface itself. One thing to keep in mind, by the way, is that a thick rope, it should intuitively have a slower wave speed because it has more mass per length, and it was tension divided by mass, I believe. Let me make sure I got that formula right. Yeah, linear mass density, that's what I mean. The linear mass density is higher, so it'll have a slower wave speed. Anyway, let's go back to the lecture. So I promised at the beginning of this whole business with wave reflections is that we'll get to standing waves. So let's go back to standing waves. By the way, hopefully you guys are aware that lecture is going to go probably a bit longer than usual, depending on how far we get because of the quiz, and that'll be the standard process for Wednesdays. If you can't stick around, remember the lectures are recorded and the notes will be posted. So how are these relevant to standing waves? How are reflections relevant? Well, we can use reflections to form perfect copies of waves traveling in the opposite direction. Right, if you have discussion right after this, you can leave and just catch the last 20 minutes if you can, like online. So the fact that we can use reflections to form copies of waves, or alternatively, by the way, like discussion's also not mandatory, so you can just download the file and work on it yourself or come late or whatever. But it's totally up to you. So the fact that reflections form copies of waves traveling in the opposite direction, that's what we needed in order to get a standing wave. You needed one wave going one way and another wave that was otherwise identical traveling in the other direction. So what we do is that we form standing waves by reflecting off of two boundaries. So you put a wall on either side, and either end can be fixed or not fixed. Yeah, either end. Sorry, I was reading the chat and talking at the same time, which is not a recipe for good things. Either end can be free or fixed. It doesn't matter, you'll still get a standing wave. But however, whether it's free or fixed, that determines your boundary conditions for your standing wave. Oh no. Sorry, one sec. So So basically what happens is you have two walls, and you have a wave that starts from one wall, maybe it goes like this, and then it reflects off, and it does whatever it'll do, and it'll self-interfere and form a standing wave, and they'll just keep bouncing off back and forth, and it'll form a standing wave. Now, anytime you have a standing wave, you can talk about nodes and antinodes, right? So imagine, for example, that we had a standing wave that looked like this, and it was just oscillating up and down. So a node is a place where the displacement just stays whatever it is. An antinode is the place where is the place of maximum oscillation. So if we want to talk about harmonics, which is what we're going to do, you'll want to be able to say something about what number harmonic is this standing wave. So if you want to say the harmonic number associated with the standing wave, you count the number of antinodes. By the way that we produce standing waves in almost all of our experiments is precisely with this sort of procedure. We just take two barriers, two medium changes, maybe they're two metal plates for sound, or maybe it's just maybe we just tie off the string on two ends for a string oscillation, and then we just do stuff to the stuff in the middle, and that will form a standing wave because of these reflections. So in general, if you want to say that something is the second harmonic of a system, that would mean that it has two antinodes. There's a special name for the first harmonic. It is known as the fundamental harmonic. This is the standing wave with fewest antinodes. So the picture here is, imagine that you now just have a set of walls, and maybe you have a string tied between those two walls or something. You can do stuff to that string to make standing waves form. You could pluck it in multiple places at the same time. And eventually, assuming there's no frictional losses or anything, eventually you'll see, depending on how you pluck it, you'll see certain oscillations occurring. You'll either see the one I drew above, or you'll see one that's slightly more confusing that looks something like this. It's just oscillating up and down in one place. And so we can characterize the different standing waves on in a system by talking about the harmonic number associated with that standing wave. So, and the way we do that is we just count the number of antinodes in that standing wave. So, in particular, the nth harmonic, that is the name that we give to a particular standing wave in a system, is the standing wave with n antinodes. Or equivalently, it is the standing wave with frequency n times higher than the fundamental. So the frequency of a standing wave is just it's just 1 divided by the period, where the period is the duration, or is how long it takes to repeat the pattern, right? So if it took 2 seconds for, say, let's look up, scrolling up to look here. If it takes 2 seconds for this point to go down and then back up, then the period, or then the frequency would be 1/2 hertz, a half of a hertz. And so you could then just, I mean, this isn't the fundamental, but you can figure out the frequency of the nth harmonic just by multiplying the frequency of the fundamental by n. That was the whole point that I was making. So let's look at some particular examples. I know that this has all been very, very theoretical. I've kind of just thrown words at you. Let's actually start looking at various types of standing waves on strings. So let's first look at this scenario where we have two fixed ends. So we're just imagining string tied to something. In this case, it's two walls, but in other cases, one will be a wall, one will be a pole, and so on. So for two fixed ends, we always have to meet the boundary conditions, right? So we always have to have that the string has zero displacement on either end because the ends are fixed. That is the reflection boundary condition that we have. We have a fixed end, and they're both fixed. So the fundamental would look something like this. It would just oscillate up and down. We know it's the fundamental because it has the fewest number of antinodes. It has 1. We can also look at the same system, two fixed ends, but a higher harmonic. This would be probably the most obvious one, but it is in fact the second harmonic. Why is it the second harmonic? It has 2 antinodes, and similarly we could check that the frequency has to be twice the frequency of the fundamental. One way to check that is to think of, well, where do these waves come from? You can fit a full wavelength between the two. You can fit one full wavelength, right, between the two ends. Here you can only fit half a wavelength between the two ends, and because the wave speeds are the same, it's the same medium. The only thing that can be different is the frequency, because we know that frequency, speed, and wavelength are all related to each other. So here the frequency has to be double because the wavelength is half. So you can also think of the nth harmonic as being the harmonic with a wavelength of 1 over n times the wavelength of the fundamental. All right, great. What about the next, perhaps more the next obvious choice for a setup where you have 2 free ends? So remember, this does not mean that the wave can propagate outside of your region. It just means that the waves can go up and down on the sides. So what would that look like? Well, for 2 free ends, I'm going to draw my boundaries. Here, our fundamental would look like this. Oh, this is always so hard to draw. See if I can do this right. So things get a little bit messy when we start talking about free ends because it's not quite clear what we mean by an antinode. Just think of, just make sure that an antinode, or that every time you count an antinode, if it's on the boundary, like these are both on the boundary, they only count for half an antinode. That's the easiest way to think about this. Otherwise, it just gets kind of messy. So clearly there's like 2 places where you have maximum and minimum displacement, but they're both on the boundary, and because it's periodic, you can just treat them as a single place. That's the only way I can think of it. Anyhow, this is the fundamental. This is what the fundamental standing wave looks like when you have 2 free ends. Now we can do the same for the second harmonic. Here we have, let me draw my midpoint again because it's easier. Right, yeah, so counting antinodes can be easy if they're not on the edges, but see how there's 2 antinodes? There's quote unquote 2 antinodes in this case. Well, because the antinodes are on the boundary, they only each really contribute to half an antinode because they're kind of the same place. The boundary, think of the boundaries as like overlapping with one another, wrapping it around into a circle, then they're the same place. So those 2 antinodes really just count for 1 because they're both on the boundary. And it'll actually be more clear for the second harmonic. The second harmonic would look something like this. And again, we have what you might think is 3 antinodes, but there's 1 regular antinode in the middle. And then there's these 2 boundary antinodes. So again, we just have 2 antinodes. So this is the second harmonic. And by the way, we can look at this again and think, how do the wavelengths differ? Here, for the fundamental case, you have exactly a half of a wavelength, right? It goes from high to low, but it doesn't go back to high. In this case, we have precisely 1 full wavelength. It goes from high to low, back to high. So again, we have a wavelength that's half as long for the second harmonic, which means that the frequency has to be twice as large. Now, there's one more thing that always confuses people. if we have one free end and one fixed end, what do? Well, so we know that one side has to just be fixed. So let's just, without loss of generality, just say it's the left side is fixed. What is the right side going to do? Well, the right side has to be at one of these antinodes, right? Because it has to be allowed to move freely. And so what you end up with is actually just a shape like this, where it's just the left side is fixed, the right side just moves up and down. So here is the fundamental. And now the second, the higher harmonics get weird. So again, the left side has to be fixed. Come on, draw. The right side has to be at an antinode. So the only next one that we can fit is one that looks like, oh, that's terrible. Is something like this. So now you might say, okay, well, what do we do here? Well, this one, again, it only has half of an antinode. Okay, how many antinodes does this have? I'm going to put this in quotes because we don't actually talk about it that way, but it's a good mnemonic. How many antinodes would this one have? Well, it has one regular one, and it has another half. So this has 3 halves of an antinode. So in fact, this thing that I've drawn is the 3rd harmonic. Because it has 3 times as many antinodes as the first, as the fundamental. And this is, it's therefore more clear how many antinodes it has, or sorry, what harmonic number it is, if you just think of it in terms of frequency. This has a wavelength of, say, L over 4. You could, it goes up, but it doesn't go back down to the middle, and it doesn't go, like that is, if you were to draw a wave, like this, that is only this first quarter. So so the wavelength there, sorry, it's 4L. The wavelength here is 4 times the length of the cavity. Right, so I'm getting to that, here, the wavelength is, well, there's 3/4 of a wavelength fitting in L. So the wavelength here is 4L over 3. Because if you multiplied that by 3/4, you get L. So here you can see that the wavelength is a 1/3, and so the frequency would have to be triple, hence 3rd harmonic. So the point here is that there is no 2nd harmonic for the boundary conditions where you have one free end and one fixed end. There's no way that you can fit that. It would have to have a wavelength of 2L, which means that you'd have to be able to fit exactly half a wavelength between the 2 ends, but that cannot happen if one end is fixed and one end isn't. Because exactly half a wavelength means that both ends have the same property. If one end is fixed, the other end is fixed. If one end is free, the other end is free. Which is, I mean, it's just a feature of these boundary conditions that we've imposed. Fortunately, there is a formula for figuring out the wavelength of a given harmonic, right? And maybe you figured this out by now, that you take the fundamentals, you take the wavelength of the fundamental, and you just divide it by the harmonic number, right? So in this case, this top case, we had a wavelength that is half as long as the wavelength in the fundamental, and it was the 2nd harmonic. In this case, we had a wavelength that was a 1/3 as large as the fundamental, so is the 3rd harmonic. So there's a pretty obvious pattern emerging. We get a formula for wavelengths of harmonics. Unfortunately, there's actually 2 formulas, one for where the boundary conditions are the same and one for where the boundary conditions are different. So the first formula, lambda n, is just 2L divided by n. This is for when both ends are the same, either both free or both fixed. The other case that we have is lambda n equals 4L over 2n minus 1. This is for one fixed and one free. The reason they have to be different is because while the two free ends and the two fixed ends have the same fundamental wavelength, the one fixed, one free just doesn't. And you'll notice that there is no fourth harmonic for the free end either. I want to make sure that so there is a caveat here in this formula because I haven't really told you what n means. So just as a quick note, while n counts the nth, I need a th here, harmonic for the first formula, in the second formula, this is basically telling you what n means. It describes the, I'm going to put this in quotes, 2n minus 1th harmonic for integers n. So the point that I'm getting at is that if you were to look at the wavelengths for the harmonics for both ends fixed or both ends free, you just look at, okay, well, the wavelength for the fundamental, you plug in n equals 1. Wavelength for the second harmonic, you plug in n equals 2. For the third harmonic, you plug in n equals 3 into this first formula. For the for one end fixed and one end free, the harmonic number is this 2n minus 1. So if you want to figure out what the if you wanted to find the wavelength of the third harmonic, you would plug in n equals 2, because if you take 2 times n, which is 2, and subtract 1, you get the third harmonic. So you'd plug in n equals 2 to get the wavelength of the third harmonic. You'd plug in n equals 3 to get the wavelength of the fifth harmonic, n equals 4 to get the wavelength of the seventh harmonic, and so on. And that is for the one end fixed, one end free. I suppose you could just write lambda sub n equals 4L over n. However, that would indicate that n can't be even. In this case, n is just always an integer. It's always just 1, 2, 3. And if you wanted to figure, and that will give you the sequence of wavelengths. But in the second case, n is not equal to the harmonic number. You have to do 2n minus 1 to get the harmonic number. Just a little bit of information that you guys will need. I know it can be confusing with this whole business of one end fixed, one end free. I just wanted to make sure I clarify that. So great. We've talked about how you can get standing waves from reflections. We've talked about the types of standing waves that you can get in various cases by forming these cavities. That's what they're called. We've talked about harmonics, but we haven't really talked about anything that's real yet, right? And in order to do that, we need to get a little bit mathy. Oh, come on, scroll please. There we go. So we need to talk about Fourier decomposition. It's not Fourier. It's not more Fourier than the other thing. It's Fourier. It's a French name. Fourier. I don't know. I'm not French. So we need to use Fourier decomposition to answer the question: what happens if you put a wave with a non-harmonic frequency between two fixed ends? So the idea here is that, assuming there's no friction or anything, if you just started off with your string and then you instantaneously deformed it to be in this shape and then let it go, it would just oscillate like that forever. But notice that in order to get that sort of standing wave behavior, you have to start off the wave in the conditions where it is already in the shape of one of these particular harmonic waves, one of these harmonic standing waves, right? But you could imagine you have a string. Imagine that you have a string tied off on either end, and then you just pick it at one end. You pinch it at one end so it bends here. Maybe come on, I can draw better than this. You lift it up here, and then let it go. Well, that's not assuming that these are fixed. That's not any of the harmonics. So the question is what happens? What happens to that wave? Does it just go down once and then stop? Well, no, because the wave is still going to propagate. It'll still go left, it'll still go right, it'll reflect, and something else will happen. The question is what happens? So far, all we know how to handle are these harmonic waves. So it turns out every wave, underline that, every wave can be written as a sum of harmonic wave functions. And by the way, that's true regardless of whether or not the waves are standing or not. If you just have any old wave function, you can always write it as a sum of sines, or a sum of cosines. Sum of harmonic wave functions with various coefficients. And what I mean by that is if you have some wave function, say f of x and t, you can always write that, it is mathematically possible to write that as a number, call it C1, times one harmonic wave, plus another number times a different harmonic wave, plus a third number times a third harmonic wave, and perhaps all of these have different wavelengths or different frequencies or whatever. But in particular, this can be done where f sub n of x and t is the nth harmonic. Or in the case of where it's one free end and one fixed end, it would be the n plus 1 over 2th harmonic. Basically, you would skip 2, 4, 6, 8, and so on, because those harmonics don't exist. But the point is you can do this. This is something that there are formulas for deriving that result. And we can obtain these coefficients relatively easily. It just requires a little bit of calculus. And this is via the method of Fourier analysis. So if you've talked about Fourier analysis in your calculus classes, this is what you were doing. It's similar to a Taylor series, but it's a different type of series expansion. Instead of expanding about a point, you're expanding about a frequency, is basically what you're doing. So the point is you would start off with this triangle shape here, and then you'd say, okay, well, how much of that wave is the first fundamental, or is the fundamental frequency? Well, the fundamental looks something like this. So it's mostly that with a little bit, but it's a little bit lower here and a little bit lower here. So how do we fix that? Well, we'll have to add some amount of the second harmonic. But that still won't be quite right because that will raise up one side and lower the other side. So how do we lower one, and hopefully you guys get the idea that you're basically just adding more and more of these waves to more closely approximate the wave that we're doing, and in the limit where you have all of the harmonics, you get precisely the wave function that you started with. So, okay, great. So far we've talked about what standing waves are, how they're formed. They're formed by two identical waves overlapping. We've talked about how to generate them via reflections. We've talked about what the harmonics are, what the special standing waves are that just have a single wavelength for given scenarios. Both ends are the same, both ends are different. We've talked about how to go from any arbitrary wave to a sum of different harmonics that will propagate at their own rate. What's the next step? The next step is to talk about the energy in a standing wave. So let's do that. We already know how to talk about the energy of a regular wave. So what about the energy in a standing wave? So there's a bit of a paradox here, and I'll describe what I mean. So, oh, scroll for me, there you go. So consider, say, the second harmonic for fixed end standing waves. So we're imagining the second drawing that I did. Just to refresh your memory, we were imagining a wave that looks like this. So how do we form that wave? That is formed by having two oppositely traveling waves, each with amplitude A. Right? That's how you form the standing wave. You have one wave going left, one wave going right. They each have their own amplitude, and you get double the amplitude coming out. So let me draw a quick picture. One wave like this, another wave like this going this way. And so they'll overlap, and then they'll reflect and overlap and cancel out and add up and cancel out and add up, and so on and so forth, right? So you might say the total energy, we already know that the total energy is proportional to the amplitude squared, right? That's a thing that we learned earlier. Total energy is proportional. But we also know that energy is conserved, by the way. So the total energy should just be the sum of the energy of each of the waves. Or the total energy is, I will say it is sum of energies. So we might get that the total energy is proportional to A, because the total energy is proportional to A squared for a single wave, plus A squared, which is just 2A squared. So the total energy should be proportional to 2 times the amplitude squared. However, here's where the paradox comes in. A standing wave has twice the amplitude. So that would indicate that the total energy, which we know is proportional to A squared, should be proportional to 2A quantity squared, which is 4A squared. Now, both cannot be right, right? There's an issue here. Our assumptions are failing somewhere. And the failure here is that the fact that the total energy is proportional to the amplitude squared is true about single waves. But a standing wave is not a single wave. Right, we talked about this earlier. It is a combination of two waves traveling in opposite directions. But why does that matter? So in a wave, in a normal traveling wave, sorry, in a standing wave, each individual particle that makes up the medium, think like a segment of rope, doesn't have the same amplitude of oscillation as the others. So the picture here is, let me copy this just so I don't have to keep redrawing it. Benefits of teaching online means that you don't have to, that you can copy and paste, which is nice. So if we look at the particle that's at the antinode, it has an oscillation that's 2 times the original amplitude of the original wave. But if we look at a particle that's not at the antinode, it has a smaller amplitude. And if we look at a particle at the antinode, it has 0 amplitude. So whereas before, when we computed the energy, in order to find when we computed the energy based off of this whole spring model, I can scroll up. When we computed the energy based on the spring model, we assumed each spring had the same amplitude, but that's just not the case here. Instead, to find the total energy, we have to have to integrate the energy of each particle to find the total energy. So we didn't have to do that before because all of them had the same amplitude, but now the amplitude is varying with position. And so we can't just add up an infinite number of things and then just not worry about how the amplitude changes because it was constant. It's basically like we were integrating a constant before, now we're integrating a function. So just as an aside, let's just talk about a regular wave again. For a single traveling wave, the energy was 1/2 mu lambda. This is for a single wavelength, by the way. Omega squared a squared. And this is the mass of the string segment for 1 wavelength's worth of string. For a standing wave, you could work out this integral yourself if you want to. It's really not that hard. The total energy works out to be, again, for a single wavelength's worth, it is mu lambda omega squared a squared, which is precisely twice the energy of the single traveling wave, which makes sense because it should be energies conserved. So these two things, it checks out. Now the last point to make is, and actually it looks like we're probably going to finish on time, which is surprising. The last thing is that is useful to add or useful to point out, or let me try rephrasing that again. If I could talk, what would I say? The last question that you might have is, okay, we know how to start a standing wave going. You just magically magic the string into whatever shape you want it to be, and then you just let it go. But how do you increase the amplitude of a given standing wave once it's already going? Well, it's actually fairly straightforward. Remember that standing waves, assuming there's no friction, will just keep going forever. However, you could still drive them, right? You could still have something moving up and down that would follow the same motion of the standing wave, but add energy to it, make its amplitude higher. The way you do this is you just drive the wave, maybe with like a piston or something, at a harmonic frequency. You do it at whatever frequency you want to add to the amplitude to. So the picture might be, you have an oscillation like this, and then tied to one end, you have a piston or a machine that's allowed to, that pushes up when it's going up a little bit and pushes down when it's going down a little bit. That will increase the amplitude more and more. In fact, this is very, very similar to what happens when you have resonance in like building and civil engineering. Basically, what happens is because of the wind or because people are walking or whatever reason, you are adding energy to the system at precisely the right frequency that is a harmonic frequency for your system. And so the oscillations in the system will get larger and larger until it catastrophically collapses. Do I want to, how many pages of notes do I have for sound? Like, I don't know how many pages this is. I think it's like 7 or 8. It actually might just be 6. So okay, so I'm gonna stop there then. That's good timing. We actually finished even a little bit early, so I guess I had less lecture material for today than I expected. So I'm gonna stop recording.